the last video, we introduced Newton's first and second laws of motion. And in the restatement of Newton's second law of motion, remember the correct statement is that the net force on an object will equal the time rate of change of that object's momentum. But since we haven't defined momentum yet, we said that most of the time we can write Newton's second law as the acceleration of an object equals F net over m, where m is the mass of the object. Now, if we sit and think about that for just a moment, this is actually a little different idea of mass than what we've seen before, which was that thing that a balance measures. So let's get into how it is that we can measure mass, how these thoughts of mass are actually slightly different, and then we'll talk about how we reconcile that. So you'll start by just thinking about practical ways that we can measure forces. So practical measures for forces. Oops. Forces. A lot of materials exhibit a property called elasticity. And for at least a small region of it, if you stretch the material will exert a force that's proportional to its stretch. So for instance, a spring. If I were to pull on a spring, and I actually have to pull on it on both ends, usually like one end is a wall, fixed support, whatever, but I'll pull on it with a force F on both sides. When I pull with that force, what will happen is the spring will stretch, and here, let me just redraw it slightly, maybe like that, and the extra length that we gain from the stretch, this distance delta x, is proportional to the force that was applied to stretch it. Now, later we'll see that this works for most materials for a certain region, and then there's another region where the force in the stretch will still, if one increases, the other will increase, but it won't be proportional anymore. And then you'll get to a point where you just plain either bend or break the thing. But for pretty much any material, there is a region where if you tug on it, the amount it stretches is proportional to how hard you tug on it. And springs are carefully engineered to exhibit that property for a good long time. So a way that we could imagine measuring mass would be, say, to set up one of those cart and track experiments. So we have a motion sensor here. We go ahead and take a cart that is 1 kilogram. Let's say we took the international prototype of the kilogram and melted it down and turned it into a cart. Don't try that at home. I believe that's still an international crime. But hypothetically, if we were to do such a thing, we could make a dynamics cart that was exactly 1 kilogram. And then we could attach a spring to it, and then we could pull on it. And we could measure the cart's acceleration. And we would tune the pull until it was going at 1 meter per second squared, and we would measure its stretch. Accelerating at 1 meter per second squared, the force will be 1 kilogram times 1 meter per second squared is 1 Newton. Okay, and then we could repeat this process again. We could take our 1 kilogram cart, and we apply a bit bigger force on it. And we'll say get it so that it's accelerating at 2 meters per second squared. Well, then that would be a force of 2 newtons. And we could measure that stretch, and that stretch will be more than the last stretch. Whoops, try that again. So that stretch would be more than the last stretch, like so. And we could repeat this for a whole sequence of applying forces and carefully applying those forces until we get a targeted acceleration. And we can keep measuring the stretch and put tick marks on a scale next to the spring. Basically, we're making a spring scale. And then eventually, because of this property where the spring stretch is proportional to the force, we could eventually add additional tick marks in between all of the calibration tick marks. So let's say if I exerted 1.7 newtons of force, I could read that off the tick mark. All right, so let's imagine that we've done such a thing. Then, if I wanted to measure the mass of an object, and this, I'll call this the inertial mass of the object. I could imagine doing it something like this. So I would have a dynamics cart of unknown mass I want to find. Again, I'll have a motion sensor hooked up. And then what I will do is I will apply a sequence of known forces. And for each one of these known forces, we would see it accelerate at something. It would be a different value each time. Now, if we remember, as long as we're quite confident the mass of the thing isn't changing, and as long as we don't have this movement at relativistic speeds, we can use our almost always true version of Newton's second law, A equals F net over M, which in this case would be just our one applied force over the mass. I could rearrange this to be F equals ma. What would that do for me? Well, if I make a plot of the applied forces against the accelerations like so, and don't get your tail in a twist here and say, wait a minute, the manipulated variable is the force and the responding variable is the acceleration. Shouldn't it be the other way around? A lot of times in physics we'll make it so that whatever equation we're testing, the variable is the variable on the left-hand side of the equal sign is on the vertical axis, and on the right-hand side is on the horizontal axis, which is what I'm doing here. But if you want to do it the other way, knock yourself out. It'll just make the analysis just a shade trickier. So let's say I do that. Boop, 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 something like that. Then what I can do is I can run a fit line through my data. And I know that I would need to include the origin. Because if I don't apply a force, it just sits there. So in this case, the origin would be the absolute best piece of data I have. Now, if we think back to the equation for a line, so call the equation for a line as y equals mx plus b. Now here, annoyingly, this m is the slope, this m is the mass, so don't get too strung out about it. I can kind of fit this to this. I put my force on the y-axis. Okay, those check. I put my acceleration on the x-axis. Those check. Since the origin was the best piece of data I have, my y-intercept is 0, so it turns out that my slope is the mass. Alrighty. So it's just a coincidence that the letter happens to be m, but that works for us. So I can find the slope of my fit line and say, that's the mass of my cart. And what I will have done is I will have measured the inertial mass, which is how hard is it to change an object's velocity. Oops. Object's velocity. Okay. And so that's what this mass is telling me. If you think about it, that's not what we saw before. When we talked about mass, we operationally defined it. The operational definition of mass is, measuring. It's what we call the gravitational mass of the object. So in this arrangement, what the experiment that we would be imagining doing is we would have a balance beam of, just imagine like a pan balance or something like that. So I have two pans, have my unknown thing here, and I have a reference standard weight over here if I'm using secondary standards. Or if I want to get all fancy about it in light of the new SI, instead of this being another weight here, I would be applying a known magnetic force. Now you think what I'm doing here is I'm actually comparing the gravitational force here, and if I'm using a secondary reference standard, I would be comparing it against the gravitational force here. Or if it's the primary standard, where we're using a Kibble balance or Watt balance, as it's also known, I would be looking at a known magnetic force that I would be applying here. But either way, what this is doing is this is measuring how much gravity interacts with an object. So this is a bit weird. I mean, think about it. We got mass is playing what we're calling mass. I mean, this isn't just two different roles. This is basically two flat out different definitions. The M in Newton's second law is the measure of the object's inertia. The bigger the inertial mass, the harder it is to change the object's velocity, the harder it is to accelerate it. Flip side here, what we use a pan balance for is measuring the gravitational mass, which is how hard it is, how much gravity interacts with an object. So here, the higher the inertial mass, the lower the acceleration for a given force. Here, the higher the gravitational mass, the harder Earth or some other planetary body will pull on it, or actually anything will pull on it gravitationally. So that seems to be two really different things, but here's the kicker. There have been very, very accurate experiments done where the inertial mass and the gravitational mass of an object have been measured simultaneously. And here's the deal. It seems like they're equal. The best experiments to date, if these differed by even 1 part in 100 billion, we would have been able to see the difference. We haven't. That's not to say that it might not differ at the part per trillion or the part per quadrillion level or something like that, but at least at the part per 100 billion level, we're not seeing any difference. So we're going to assume And the whole physics community has assumed that these quantities are equal. So going back to Newton's second law, A equals F net over m. This mass is our inertial mass. And for our force of gravity, if we're near the surface of the Earth, it's the gravitational mass times the gravitational field strength. So if we look at an object that's in free fall, so revisit free fall. We remember that we said that the object was accelerating downward at 9.8 meters per second squared. So we can see where this is happening. If an object is freely falling, the only force acting on it is gravity. That's the definition of free fall. So, following Newton's second law here, let's just say, we'll make down positive just to make life a little easier for us. The acceleration will be equal to the net force, which is just gravity. In this case, there's only one force, divided by the inertial mass. But force of gravity is going to be the gravitational mass times the gravitational field strength over the gravitational mass. And I think at this point it's over the inertial mass. So I think it's worth a point here to just say mg and mi, just so we're aware. This is the gravitational mass. This is the inertial mass. So the reason that we go ahead and cancel these is we cancel them due to experimental observation. We assume that these two masses are equal, and then that's why we get that all objects near the surface of the Earth accelerate at 9.8 meters per second squared, for instance. It's more correct to express the gravitational field strength as newtons per kilogram, but that's dimensionally the same as meters per second squared. So we just assumed this equality. Einstein took the idea and ran with it, and came up with a natural explanation for why these should be equal, which led to his theory of general relativity, which is our current best model of gravity. Now, treatment of that is a little more than it's probably worth to go into here, but just to say that this experimental observation that these two quantities seem to be equal has helped to give us maybe a bit better understanding of what's going on with gravity. Alrighty, so in the next round of videos, we will be doing more in the way of tying forces together with motion, what we call dynamics. We'll catch you over there.